Series 2020. CMKL is established as a collaboration between Carnegie Mellon, CMKL Thailand, and KMITL. We aim to expand research and education in the areas of information, computing, and autonomous technologies. Today, we're so excited to have Dr. Limin Jia, an associate research professor in the ECE department at Carnegie Mellon University, to give us a talk on the topic of from IFTTT to XSS. It's all about the information flow lattice. So at the end of Dr. Jia's presentation, we'll have a Q&A session. So please type your questions in the chat box, or you can also unmute yourself at the end of the presentation to ask questions. So now I'll let Dr. Jia take over the talk.
Thanks. So basically, I think in the talk, I might pause in the middle. If you have questions in the middle, if I pause and ask a question, feel free to type in the chat window or unmute yourself, ask question as well. All right, so a little bit more about myself. So I got my bachelor degree in computer science and engineering in China, and I got my PhD in US from the CS department of Princeton, and then I joined Carnegie Mellon I came to Carnegie Mellon in 2009 as a postdoc. So now I've been working for CMU for a long time. Actually, I used to be associated with INI, so I haven't updated that slide. So now I'm my sole affiliation with ECE and also Scilab. In terms of research, my PhD training is in formal methods. So my research is focusing on applying these formal method approaches to ensure a system being secure. That include analyzing systems for its security properties or finding vulnerabilities, and also applying these methodology to build better, more secure systems. In terms of teaching, so I'm teaching in the fall. I always teach this introduction to information security course. I think in the Thailand program, there's a corresponding course. So I actually had communication with the instructor. The content we teach are similar, not exactly the same, but a very similar topic. So today's talk actually expand on one of the lectures. The foundations of the research, the theoretical part of research is actually based on a lecture content in this class. It's a classical notion about multi-level security. So it's kind of seeing how the formal foundations relates to security issues. So I used to teach browser security for a couple of years. So I used to teach that in the spring. Last spring, I taught a undergrad ECE course, which is digital design. The coming spring, since I'm research faculty, my main focus is on research. So I won't be teaching in the coming spring. I'm hoping to spend more time doing my research. All right, so that's about me. So let's start today's talk. So as I mentioned, this problem about multi-level security is actually quite an old problem. We actually covered this topic in the information security lecture. So the idea being in the government or in the military setting, there's a whole bunch of documents, whole bunch of files, and then you have a different personnel in the organization trying to access these files, right? So these files are of various importance. And your personnel also have different level of quote unquote security clearances, right? You can imagine if you have an intern coming in, the intern obviously shouldn't have access to the secret documents, versus if you are a 5-star general, you should be given to these documents, access to these documents. So typically here it's naturally to think that if you think about the content of the file in terms of the type of secret containing the file, there is different levels of secrecy being contained in the file, right? So for example, I give an example of 4 levels. On the bottom, we call it open or public. Maybe here there's nothing to hide. This is public information. And on top of that, you might have a level that's called confidential. That means that you contain some secret information. It shouldn't be known to the general public, but it's not like top secret, right? So for example, maybe the military purchases, what kind of weapon you're buying, things like this. Obviously, you shouldn't let the general public know, but compared to the next two I'm going to talk about, it's not as secretive. And then on top of that, we might have a little more secret information. Let's call it secret. Maybe we can classify them as information. If compromised, maybe we're putting human lives at risk. And then on top, we have top secret. So basically, these are national security level secret that you should really guard it with most care. So that's the basic notion of multi-level security. That's basically stemmed from a really concrete problem exists in government, in military, thinking about how do they protect access to their files. All right, so that's a problem. In terms of solution, so the first, so far I've been only talking about secrecy. We're talking about the files might contain secret information. So one solution is proposed very early on. I believe this should be in the 60s even. So this model is called BLP. It's Bell-LaPadula model, shortened to BLP model. So the BLP model is meant to enforce multi-level security to protect secrecy. It has two properties. So the first one is called the simple security property of BLP. It's talking about who can read what. So now what you imagine is that you have files being given various labels based on the security level, right? So I have a file that's labeled top secret in this example. You might also have other files labeled being public or open, or other files being labeled secret and so on. And then for the personnel, for the people who want to access these files, these people are also given a label, but typically these are called clearances. So for example, if you are the US president, you will be given top secret clearance. Notice that I didn't use the current president's picture for a good reason. You will see in a little bit. So basically, this represents the president of US for now. And then we have on the right, we have somebody like Homer Simpson who has no clue what's going on. It's just a general people. Homer doesn't have any clearance to access anything. So what BLP model, the simple security properties enforcing is talking about who can read what. So basically, if you have top secret clearance, if you match the label with the file, this file I have on the slide is also top secret. Let me get my cursor. If these label match, then the read access is granted. All right. So this is common sense, because if you don't have the proper clearance, you shouldn't be able to read the file, right? So the other side of the example is that if you look at Homer, Homer has no clearance. Therefore, when Homer try to read this file label that's being top secret, this access should be denied. All right. So that's a simple case. So I simply said the label should match, but in reality, it's not a simple match. So instead, what we say is that the label have levels. As long as you have a clearance level higher than the file, then you can read that file, right? So the example is that instead of a top secret file, here, if I have a secret file, here, if the president has top secret clearance, the person who has top secret clearance can also read secret files. All right. So it's here, Homer can still can read secret file, because this no clearance means Homer can only read open or public files. If you compare the label of Homer and also the file you're trying to access, Homer's label or clearance is not equal or higher than the label of the file. All right. So that's a simple read policy. So I'm going to stop quickly. Anybody have a question about this read policy? All right. In that case, I'll move on. So this is about reading. Typically, the access in addition to read, you also have write to files, or write to a channel. So in BLP model, this policy is called the star policy. So here, I actually used Twitter as an example of a channel you can write into, right? This can be a file as well. Given social media time, I'm just gonna use Twitter as an example. So the tweets are public. So this channel, the file that the data you write into Twitter is actually considered public or open. All right, so that's had the lowest secrecy level on the multi-level grid that I showed you in a couple slides ago. All right, so now the president has top secret clearance, meaning that the data that the president writes may contain secret. So the star property is saying that if the data being written to a file, when we compare the label, we have to make sure that the data being sent to the file, this label has to have a lower security level, lower or equal security level than the file or the channel that data is about to be sent to. So here, the person with top secret clearance actually cannot write to a public channel, because this data contains secret information. all right? On the other hand, on the right hand, you have Homer. Homer knows nothing about important secret. All the data that Homer tweets would be labeled public or open. If you compare these two labels, this is fine. So Homer can tweet publicly to Twitter that this data will be seen by everybody. So that's the right policy. It's called the star policy. Here, this is common sense again. What we're trying to do is we're actually trying to prevent information leaks. All right. So this is also the reason why I didn't put the current president on the picture, because obviously we know that the current president tweets a lot. So this example wouldn't go down very well. But in terms of security, the good practice is that for data that may contain secret shouldn't be written into a source, either a file or a public open channel in the network to a public channel that the attacker or the general public can see. All right. Any question about this policy or the property? All right, so if there are no questions, I'm going to move on to talk the other side, yet another aspect of the multi-level security. So when I started, it's very easy to motivate to think about the file might contain secret information. So this is about protecting secrecy. But the other side of security, the dual of secrecy, is something called integrity. So BLP actually doesn't deal with integrity at all. So instead, we need yet another model called the Biba model that's trying to protect the integrity of data. So typically, the way to think about integrity is that when you try to enforce integrity, you're trying to protect attacks against trusted data. You don't want the attacker to mess up with data source that you have to trust. All right. So here again, I'm just going to show this through example. The way to think about this is that again, we have a multi-level, but I have a different meaning of this level now. Now, in the secrecy land, the level is about the level of secret information the file contains, or if you think about the humans label or the clearances, is about the type of secret this person is allowed to learn. Here, in terms of integrity, we're thinking about trustworthiness of the information. Also, for a person with clearance, we're talking about how trusted this person is. All right. So in this example, the file we're looking at is something that require. So these are highly sensitive data that actually require trusted people to put in that data. So the example I give is, for example, in a war, there are targets you want to attack, right? So the coordinate of the target that you're about to bomb. Now, these targets are highly sensitive because you don't want to bomb the wrong place. If you bomb a civilian place, that's really, really bad. So these are highly sensitive data. You require a trusted source to put this data in, all right? So that's the notion of integrity. So in this example, again, here on the left, this picture can be replaced by, if we're talking about war, it could be the generals, all the officers, trusted officers, managing the situation. So here, if this person has clearance of trusted or being trusted, then this person can write to this sensitive data, right? Versus on the right hand, we have Homer again. Homer is not trustworthy. Homer doesn't know anything about this war or where to actually attack. If Homer somehow managed to write to this data, you can imagine this will be quite disastrous. All right. So the main part about the Biba model is that controlling who can write to the trusted data source. So in this particular example, Homer is not allowed to write to this target to attack because Homer is not trusted versus this data need to be trusted. On the other hand, if you have someone who's highly trusted, then this person can write to which target to attack, all right? So typically, if you read the literature, it's called no write up. When we say up or down, this is a little bit slightly confusing in the sense that when you think about up or down, we put high integrity data or trusted people label as on top. The not untrustworthy data or untrustworthy clearance is on the bottom. No write-up, meaning if you have clearance, get my cursor back. If you have clearance lower here, you're being untrusted or can only produce low integrity data, you're not allowed to put your data into a source that requires trusted or high integrity data. So that's a policy in terms of protecting integrity. All right. All right. Any question here? So in terms of your systems, it's quite common to think about, for example, in Windows, if you downloaded the program from the internet, these kind of programs are considered untrusted. Therefore, your system going to ask you, are you sure do you really want to run this program? Right? That's for the same reason of they don't want a untrusted program to potentially modify the rest of the program on your computer, because the rest are considered trusted versus this newly downloaded program are considered untrusted. So you have to say, yes, I'm okay with running this program. If you okayed it, then your system remember, okay, now you have blessed this program you just downloaded. Now that particular program become the trusted side as well. Now that program can run and start modifying your computer. All right, so that's one thing you probably run into as you were interacting with the computer, installing programs and running programs daily. All right. So that's the basics. So that's essentially the lecture part. That's the foundations, right? This Biba and BLP model were quite well known. They were invented to tackle a quite practical problem in the government, in the military, where you have this multi-level security situation, all right? So the question is, well, this look like it's high theory. Is it still relevant? Is it relevant today? Right? I already give you an example where it's relevant. It's in your OS when you're downloading untrusted file, when the file needs to modify your system, access data. Actually, that's where BLP and Biba definitely matter. You see it subtly in your system, but maybe not upfront. From a research perspective, I'll show you two other examples that's actually quite relevant based on today's environment. So the first example is this home automation system. So basically, wait, let me see. Yeah, so basically with the introduction of IoT and all the interaction between IoT and other services, we're actually pushing information through all these different services. So here, if you think about it, things actually might a lot of these services and your IoT devices might capture private information. You're also thinking about who can control your accounts, who can control your IoT devices. From that perspective, it is in integrity side of the problem. So if you just think about it, here we do have to worry about how the information, the access of data should be allowed to flow in this particular setting. All right. So that's the first example I'm going to go through. So just a little bit a background to start. So this IFTTT is this framework called if this then that. So this is essentially connecting services with a bunch of smart devices. Let's see. I'm just going to show you really one simple example where when we introduce smart devices, when the smart devices start to collect information, if you're not careful, bad things could happen. So this is sorry. Yeah, so obviously you have malicious attack like the DNS, the Mirai attack, where the devices were hijacked to actually mount DDoS attack of other services. So that's malicious attack. There are also somewhat amusing accidental attacks. So what's going on the right is that there's there's an app called Strava. So if you exercise, Strava can essentially track the path you have run through or your bike through. You can look at your training status and so on. So back then, when people use Strava, Strava collects all this information. If you don't carefully configure your privacy setting, your workout might be shared with the public unknowingly. But what's interesting is that back then, Strava thinks that the heat map, meaning how popular a route is based on all its customer data, is considered public because there's no personal identifiable information. It's a aggregate of information. So therefore, the public heat map of path that people frequently exercise on. So it turns out that the US military use Strava app as well. So the soldiers, when they do workout, they actually track their own status and so on. So what's happening is that this is actually a US military base. On Strava, you can actually see the heat map of this military base. Essentially, you can see that there are all these paths that the soldiers are using to walk around or run around or bike around and whatnot, right? So this is completely unintended because the secret base is supposed to be secret. You're not supposed to know exactly what's the layout and where things are. It turns out these aggregate data do have implications in terms of privacy, right? So this is kind of a interesting anecdote to show that when you have new technology, we have to be super careful considering how do we put the privacy policy, how do we make sure to protect private data to not to be leaked into the wrong hands, all right? So I already hinted I already hinted when you have all these devices collecting data, you can think about this. We're going to have a lot more problem to control, to think about how the data can actually flow. So what is IFT platform? So IFT essentially allow user to connect devices and their online services, all right? Here's an example. It's called IFT because it is if something happened, then do something. So that's all the user can configure these rules. Nowadays, it used to be called recipes. Nowadays, they're called applets. So you log into IFT platform, and then you say, then the platform will suggest some of these applets that you can install into your account, and then you can achieve greater automation. So for example, what I can say is I can say if my Fitbit logs 10,000 steps, post a tweet. All right, so that's one thing you can do. This is connecting Fitbit to my Twitter accounts. So similarly, I can also do things like if I'm close to home. So typically, your phone would have a GPS. They have location tracking, and you can set where is your home. So that can be known to the IFT server based on your phone's GPS. So you can say that if I'm close to home, then turn on my Nest thermostats, right? You want your house to be heated or cooled at the right temperature when you enter your house, all right? So this is something that you can do through IFT applets as well. So it seems like it creates great convenience to people. There are actually quite a bit of user on the IFT platform. Nowadays, there are a couple of different platforms offer similar services, but IFT is still the one's most popular and has the most customer base, all right? So the question is, can IFT applet actually have harmful side effects, all right? So that's what we wanted to investigate as a research project. So just to be a little more clear about terminology, in IFT, you have something called a trigger. That's the IFT part. Then you have something called an action. So that's the then part. This whole thing, this whole if something happens, then do something, is called an applet in IFT language. So there are a lot of triggers. You have a lot of services you can register with IFT that you can program the triggers. So for example, you can, in your email services, things like Gmail, you can have triggers like if I receive a new email. You can be even more refined, saying that if I receive a new email with this subject title, right? So these are triggers. Another example is a Fitbit I already showed you, and Facebook have a few triggers. So for example, one trigger is if I'm tagged on a photo, all right? So on the right hand side is the action part. So basically you can do something with your accounts. So the example here is in Facebook, you can create a new status. You can update status on Facebook, or you can control your home IoT devices, things like Nest temperature. You can set the temperature to be a particular temperature. You can set its modes and so on. The last example is Flickr. You can upload a new public photo as an action in your IFT applet. All right. So here, it seems like there's convenience, but I'm going to give you some example where things could go wrong. So for example, I have a applet saying that take a photo. If I have a new photo, if I take a photo with my iPhone, then upload the public photo to Flickr. So what I wanted is that so this is actually a picture of Pittsburgh. This is an incline, and this is a river. This is actually something called the Point. So I'm actually on a tour. I wanted to document all the cool places I've seen on this tour. Therefore, I set up this particular rule. Once I take a photo, this is automatically uploaded, and my friends can see where I've been, all the cool places that I actually have been. The problem is that if I forgot to turn off this rule when I'm done with my trip, I came home, I need to apply for a visa or some other documentation issues that I need to deal with. I take a picture of my passport with my phone. Now this rule would actually put my passport information over on Twitter. So on the passport, there are quite a bit of sensitive information included in US. If somebody else got this information, they could actually potentially steal your identity and do other damage, right? So this is unintended consequence, but this is the same applet, right? So the problem here is the secrecy side of things. If you install an applet, there is a possibility that this applet itself could leak private information. All right. So that's one example. As I mentioned earlier, when you think about security properties, when there's secrecy, then the dual side of the property will be integrity, right? So what does integrity mean here? So here's the example to show you a little bit. So I have an applet saying that if I'm tagged in a photo, then update my status on Facebook. All right. So this rule, the goal of this rule is I'm attending a party, I'm attending a cool event. If my friends or other people took a picture of me and tagged me, I want to have that picture too, right? So when I have a new update, a new status on Facebook, I can see that photo to see that I've been at that cool place as well. The unintended consequence is that you could be that you told your boss that you are actually sick at home, you can't go to work. In reality, you actually went to the party. So here, in theory, only you should be the one who can update the status. But now here, using this applet, now you have other people to update the status. The result is that now somebody else sees that you're at a location that you are not supposed to be. All right. So this is the integrity problem, because now these I use the word recipe, which is old word. There should be applets. So basically now this applet can cause things that used to be the case that you are the only one who can cause this to happen. Now with applet, certain things you thought you're the only one who can make this happen. Now you open this up to other people to cause things to open, to be operated on. So for example, turn on your lights, turn off your lights. So you can imagine that you can have applets that allow other people to potentially control your devices. In this example, it's controlling updating status on your Facebook. All right. So these are a few of the examples that you can see that the way we look at this problem actually follow the way that the multi-level security problem is being described. All right. So what I'm claiming is that if you look at this, by and large, when we try to understand the secrecy and privacy problems in IFT, we're actually looking at a multi-level security problem. All right. So that's where the theory applies. The goal of this research is actually look at this IFT platform. When we looked at it, this platform is actually was fairly new at the time. We're trying to systematically analyze these applets for potential security and privacy problems. The foundation we're relying on is this multi-level security theory. We're trying to categorize what are the secrecy and integrity problems in the eye of multi-level security. All right. So in the talk title, I've used the word information flow security. I've been using multi-level security from the beginning of the talk, but these are quite related because when you look at multi-level security, we're actually controlling how the information can flow from one label to another label. All right. So basically, then the first thing, once we realize this, the first thing we need to do is we actually need to define these labels, right? On the secrecy side, earlier when we talk about the government documents, it's very easy to think about public secret, how secret things can be. But if you think about the IFT platform, this simple level, the way we're dealing with level doesn't work anymore. All right. So the first task is actually figure out if we look at all the IFT recipes, all the triggers and actions, what are the applicable security levels? All right. So we had our couple of PhD students essentially download all the public recipes and triggers and actions, the applets, triggers and actions, to look through them, try to summarize what are the reasonable security. So here we first look at secrecy level, then we're going to look at the integrity level. All right, so here's what we found. So obviously we want to have a label called private, right? These are information only you should be able to see. Things like if you have a health device, maybe your new weight logged in that device. And then we have a group, we have a label, we call it restricted physical. So here, basically anybody who's nearing a physical location can have access to that information. So for example, your nest temperature, right? Everybody in your house can walk by that device and look at the temperature itself. The third secrecy label we think makes sense is called restricted online. So these are your online friends that you share some information with, right? For example, your Facebook friends can see the status updates, all right? Then the last label we have is called public. So this is really anybody can see, right? For example, the weather today is a sunny day. Everybody can go to weather forecast and see this weather, or go outside themselves to see what's the weather like. There's no secret contained in this particular information. So in the previous example, when we only have open secret, top secret, this actually forms a line, right? One is more secret than the other. So here we actually don't have a straight line. Instead, what we have is a lattice. All right, this is a mathematical structure that essentially apply orders to these, enforce ordering of these labels, enforce partial order of these labels. So what we have is that we actually have two lines. What we're saying is that on the left, we have a line public, restricted physical, and private. On the right, I have a different line, which is public, restricted online, and private. So if you look at these two separate lines, you interpret it in the same way as you look at one straight line. It's just that the restricted physical and the restricted online themselves, you don't compare between them. Or they're not comparable. So because they belong to different sets of people. So when we talk about multi-level security or information flow security, what we're saying is that if you follow the arrows, that's good flow. If you go against the arrow, or if you propagate information between two things that does not have a arrow going from one to the other, that's a bad flow. That should be forbidden. All right. So what this is saying is that if I have data that's labeled private, and if I have someone only have restricted physical access, let's say clearance again, in this case, we cannot allow the private information to flow backward to someone who only have restricted physical access, right? That's a bad flow that I marked in red. You're not allowed to flow in the wrong direction. In the right direction is okay, in that if this data is public, if someone have access, this restrict online access, or just private, this public information can be given to people who have clearance either at private or restricted physical. All right, so these are good flows. If you go against the flow, these are going to leak information. So that's where the lattice comes in. So this is slightly more complicated multi-level security, because we actually have a security lattice to tell us the direction of information flow. So now let's look at some examples. So here, the first example I'll give you, take a photo on my iPhone, then upload to Flickr. The photo you're taking is actually private. When you take the photo, only you can see it. When you upload to Flickr publicly, now it becomes visible to a bunch of people, right? If you look at the lattice, this is actually the wrong direction of information flow, right? So this is actually a applet that could potentially leak information, all right? So the second example is if you have applet saying that if I enter a specific location, then upload the file in Google Drive. So this one is a little bit tricky in that when you enter a specific location, this information we classify as being restricted physical, because anybody around that location can see that you entered that location. Now, what you are doing is you actually put this information in a place that could potentially be shared by other people on Google Drive. But just by looking at this applet, when we analyze this, we don't know whether this file on Google Drive is only you privately can see it, or it can be shared, or you share that folder with other people, right? So here we have two possible labels. This one possibility is private if you set the setting not to share. It could be restricted online if you actually share this file with other people. So when we do analysis, but either way, this information flow is considered bad because we don't have an arrow go from restricted physical. Sorry, if it's restricted physical to private, this flow is okay, so that's allowed by the lattice. If you actually share this file with a bunch of other people, then this flow is bad because the people who see you enter a location is different from the set of people who can see the files online. So here you might leak information. All right. So this already hint at when you try to do analysis, this is not super easy because you need to know the contextual information about the sharing status and how the rule is used and so on. All right. So in terms of integrity, so we have similarly identified labels for integrity. I'm not going to go into detail. This is actually almost directly mirror what the secrecy label is about. So in terms of letters, we have trusted, untrusted, physical, restricted physical, restricted online. The way to think about this is who can operate your devices, right? So anybody you invite into your house can go twirl the Nest the Nest device. They can actually control that device. So these are considered restricted physical. All right. So let's see. Yeah. So similarly, in terms of information flow, this Biba model, if you follow the arrows, that's okay, right? If you have a trusted person like you yourself is operating on something that you expect anybody in the room to operate, that's totally fine. If you go the other way, it will be bad, right? If you have something that you think only you can operate on, now you somehow the applet managed to allow other people who are in a different in the same room as you can operate it. That seemed to be that could cause problems. That will be a bad flow if it's against it or if there are no arrows between them. In terms of examples, so here we have the first example again about tagging a photo. So what's happening is that anybody can, not anybody, the people who you share with on Facebook could potentially tag you on the photo. So on the left hand, you have restricted online. On the right, in terms of Facebook status update, typically you think only you can do it. So that's considered trusted. Your applet is actually allowing control go from left to right, which is against the flow of the security lattice that I just showed you earlier, right? That's why this could potentially cause issues. Another example is we have a applet saying that if there's a new Instagram photo in the area, turn my smart switch on or on then off, like you're flickering your switches. So this is a problem because this new Instagram photo in the area, anybody can post a new Instagram photo in the area. So that's considered untrusted. In terms of operating the switch in your house, you probably consider that either you or people who's in the vicinity of that switch can operate that. Again, the control or the information flow goes from untrusted to unrestricted physical, which is against the flow of the lattice that we just showed you earlier. All right. So that's kind of the modeling of the IFT platform. So then the next thing we do is we did analysis. Essentially, we go through all the applets, all the triggers and actions, assign them security labels, and then look at all the recipes, publicly available recipes at the time, and try to analyze which ones could cause potentially problems. All right. In terms of analysis, we actually wrote a analysis tool to essentially examine every recipe to see whether the triggers label is, I guess we compare the triggers label with the actions label and make sure that they follow the information flow. If they don't, we'll dump out a warning. We'll say that this recipe could potentially have issues. So we do have an automatic algorithm to actually analyze this. So here are the result we had back then. Essentially, among all the public recipes we analyzed, over half of them could potentially having issues. Here's a final breakdown. Essentially, 23% of them could violate the integrity lattice. 10% of them could violate both secrecy and integrity. So that's that means that 33% have integrity issues, and then we have another 17% that could leak secret. That means that we have 27% that could have secrecy problems. All right. So this is a really rough estimate. Like the rules I showed you earlier, sometimes depending on the setting, it could be good or could be bad, right? So for those, we count them as being potentially having issues. All right. So in terms of the takeaway here, other than the result, is that if you look at these recipes, it's really that there is a possibility that it could cause harm, and the users typically don't necessarily know what's going on. So we do think that there should be tools to help user understand what's going on here. In terms of connecting back to theory, when you try to analyze the security and privacy problem, for us, it's lucky that we have a formal foundation we can rely on to systematically say that this is a category type of problems we need to pay attention to. So in terms of future work, we actually had a follow-up user study that is published this year. We actually asked the user, essentially, here's what we think is going to have a problem. What do you think? So it's not surprising that it turns out that our analysis, because the analysis just look at overall labels, overestimate the harms, right? So for all the applet I showed you, there are situations that could be problem, but in many cases, the user knowingly do this. They know that, oh, I know what's going on. It's totally fine. Or in other situations, there are contextual information we do not know. For example, the sharing setting of the Google Drive. So for this reason, for our future work, we actually need we are interested in looking at a much finer grained way of modeling. Essentially, the lattice is too coarse grained. We're trying to figure out, actually, can we have a more precise model to tell the user precisely, ask the user, what's your setting? And then once we get the information, we can say precisely, oh, if you have this setting, then you're fine. However, if you have a different setting, you might be leaking information in these respects. So that's where we're going in the current work. All right, so any question about this section? So I think I'm slightly running out of time, so I'm just going into the second topic briefly. I guess I will not go into the details, but I do want to show you the connection between the security problem and the multi-level security or information flow security. So this topic is actually on DOM-based cross-site scripting. So essentially, cross-scripting is a very common attack. It's considered to account for 25% of the web vulnerabilities. So I'm just gonna make this quickly. So what's happening is a user is browsing, you have a website with vulnerabilities, somehow the attacker managed to craft a URL exploit. The user goes to this website, the exploited page managed to get into the user's browser. When the user actually browse a page, the browser would actually execute the attacker code that would cause, for example, secret being stolen by the attacker or some other or the worst type of attacks. For DOM-based XSS, really the vulnerability happen purely inside the client. The server is not necessarily involved, other than the server just send the page over to the client. So what I want I'm going to go on for another couple of slides and we'll stop. So here's the example of a vulnerable page that is subject to DOM-based cross-site scripting attack. So what's happening here on your page, you have a script saying that I'm going to read the URL on the URL bar. Then I'm going to take the URL and generate a link, and then I'm going to put this link on the page. For example, I'm saying you are at this website. I'm going to put that link there. The problem here is that if you look at this, we have something we call the source, where you're taking information. It turns out that you are taking information from URL. This URL could be constructed by anybody. Typically, user is the one who goes to the website, but a lot of times the attacker could have crafted this URL, right? So here we start from the source of information that could be coming from untrusted sources. And then what's happening in this program on the bottom, you are writing a markup directly based on this untrusted input string, right? So these kind of functions, write or eval, is something we call the sink. So what's happening is we see an information flow from the source to the sink, where it violates the Biba model, because at the source you are taking information that's untrusted. You are writing it or using it at the sink that require highly trusted data, right? Imagine when you write to the DOM, your browser is actually going to interpret that piece of data. If there's code in it, your browser is going to execute it. right? Similarly, if you have a eval, if you actually take string to be a script and you evaluate it, in this case, you have to pay attention to where that data come from. So basically, I'm going to stop here. The cross-site scripting attack, essentially, if I apply the theory of information flow security or multi-level security, the problem is that it's actually a write-up, which is against the Biba model's policy, which is saying no write-up, right? You're not allowed to use low-integrity data in a place where you actually imagine trusted data, all right? So this research essentially is to develop a method to identify these kind of attacks, and we essentially modify the Chromium browser to help us identify these attacks. Then we categorize them. We crawl the web page for close to 50,000 websites. Then we categorize the type of bugs we actually find. So let's see. In the interest of time, maybe I'll just show the figure that we have. Essentially, the domains this is the domains we crawled and how many bugs they have. So essentially what this is saying that most of the, very few websites have a lot of cross-site scripting, potential DOM-based cross-site scripting vulnerabilities. And then we have a long tail. Basically, a lot of websites actually just have one minor issue that could be exploited. So the other graph is that we look at the category of websites that have these kind of bugs. The top 3 of them are ads, analytics, news, and entertainment. All right. So then the last finding is we sampled a set of vulnerable websites to figure out what's the problem there. So it turns out that the web developers have minimal security knowledge. They don't necessarily understand untrusted versus trusted. So some of them simply actually didn't even bother sanitizing data. They really just do the things I showed you in the previous slides. They take the URL and directly put it somewhere and try to write it into the DOM. All right. So that's, if you take any security class, you should know that when you take something from untrusted places, you need to sanitize them. You need to check, make sure that nothing bad can be contained in this location. And then some people do some custom templating, and they thought that if I do templating, then the code would be in the format I wanted. So for example, I do some formatting. However, it does not prevent attacker from injecting scripts or other malicious code in the in parts of your template, essentially. And then the third kind is people actually do try to write some sanitization on their own. They don't use any well-known library or sanitization procedure to do it. So it turns out that people write very poorly constructed sanitizers. They are actually not useful in terms of protecting against attacks. So that's a finding. So in terms of where we are, so the technique what we are using is called taint tracking. So this is a runtime technique we use. We run the program and see whether we see potential bugs or not. That means that we can only observe one observation. So in terms of future work, what we're doing is we're trying to improve coverage. Basically, we want to cover bigger parts of the website, because when I run it once, I probably only see a small fraction of the page being executed. We're trying to figure out to apply additional technique to actually execute more parts of web page so we can find more bugs on one web page. The other future work we're doing is that this is JavaScript on the client side, right? We know it's a problem, but now JavaScript is actually quite commonly used as standalone programs via Node.js platforms. Right, so these Node.js packages, again, are contributed by developers. They don't necessarily program high-quality code, and some of them are just completely malicious. There are actually quite a few high-profile Node.js attacks in recent years. So we're going to essentially apply this taint tracking technique to identify code injection attacks. Essentially, again, we're identifying the Biba violation. We're trying to figure out whether untrusted code can reach to a place where the program actually expects highly trusted code. All right. All right, so I think that's the end of my talk. I think I rushed a little bit in the end, but essentially the overall takeaway is that I'm interested in applying formal foundations. All right, so here in this set of work I'm doing, they happen to be all related to Biba and BLP type of model. Back then it's called multi-level security. Nowadays in the research community, it's called information flow security. But the gist of it are the same. And I show you two applications of this particular model to analyzing security problems. All right, I'm going to end here and I'll take more questions. I think there are questions in the chat window. Let me just go through them one by one. So the first one is, yeah, so the question is whether it's automatic way of notifying user about potential issues. So this is interesting question. So if we're talking about one platform, then yes, so potentially we could work with, say, IFT platform. We say, okay, here is a tool that's built in, because if you're IFT user, all your rules, applets, all your configuration is in one platform. You log into the account, you can see all your rules there. So we could run our program, run our analysis tool on every user's rules, and then tell them, here's a potential problem. Do you really want to proceed or not? So in that case, yes, there is an automatic way to do this. The tricky part is that it's easy to have false warnings all the time, right? So we might have a high false positive rate, right? For example, for some of the rules that quite commonly used, we're going to flag it as being potentially a problem. The user might say, "Oh, I'm totally fine. I'm okay with this rule." Then the problem is that it could be annoying to users. The other one is the user will be trained to click on always okay, and then the tool become less useful. So that's why in the current work, what we're doing is we're actually trying to figure out a much more precise analysis, so that if we are going to, after we complete our analysis, we're going to warn the user, we want to have very low false positive rate. And also we want the warning to be understandable to the user, so that they're not confused about why this is being warned. Why this is a common applet that everybody else uses, why now I got a warning saying that could be security problems. That's the first question. Yeah, so second question is related in that we flagged 50% of them as being potentially malicious, right? So the problem is that one is we're missing contextual information, right? So a lot of the settings, sometimes whether it's a problem or not, is highly dependent on the setting, where the device lives, and how do you do your sharing setting, or do you really worry about posting the photo you've taken to share with your friends. A lot of these applets' goal is to actually share private information in a controlled way online or publicly. So one work, as I mentioned, is to make this analysis more precise. So it's not going to be like every other recipe or applet will tell you there's some problem that essentially exhausts users' patience. That's one side of things. The other side of things is we should have a way to give examples to the user to say, here an example problem, so they can understand via example whether their rule has a problem or not. And we should have a way of essentially allowing user to say that, to endorse the rule, saying that I know this could potentially be a problem, but the way I'm using it is actually totally fine, right? So in the information flow security world, this is called endorsement or declassification. You need to put it in there so that we don't repeatedly warning you about this particular problem. But this is a very hard problem. So from a theoretical technical perspective, solutions are not that hard, but when you apply to reality, that's where all the complication comes in. As for me, that's also why connecting formal stuff with the real world scenario is actually interesting, because you're pushing the boundaries of what the theory and technical tools can do to actually solve real problems. All right, other questions?
Yeah, is there any other questions from our participants? Okay, I guess that is it. So we thank you so much, Dr. Limin Jia, for her inspiring talk, and we also thank you, our participants, for joining us tonight. Our next talk will be held on November 4th, which is next Wednesday, by Nicholas Walker from NVIDIA. So we hope to see you guys again then. And by the way, we are now accepting the fall 2021 master and PhD applications, with several scholarships being offered. So make sure to check our website or email us for more information.
Yeah, and
Thank
also
you,
we're
guys.
obviously we're also looking for PhD students all the time, right? So if you're interested in annual research, when you in your application, you can specify security as your area, and then we're looking for a great PhD student from in the security area in ECE.
Yep. Thank you so much, guys. Thank you so much, Dr. Limin Jia.
Yeah, thank you. Good to
Thank
see you
you.
guys. Bye.
Bye.